Hi, this is Adam Griffin with the second video for this week. So we are going to be doing problem number 3. So this is a pretty strange problem. It kind of takes a lot of reading to figure out what it's asking. But so it goes like this. We have an oscillator with mass m and spring constant k and is driven at a frequency WD equals W0 equals our square root of our spring constant divided by our mass. And we assume that the external force F of t equals F0 times sine of our WD up here times t. So if the oscillator is subject to a damping force given by Fd equals negative b times the function of our velocity, find the steady state amplitude A in terms of any of the following. And so we start with our equation for force. Force equals mass times acceleration, and we rearrange it to get this equation right here. So we start off with our equation right here, and then we solve for F on this side. So our force is equivalent to all of our forces combined. So the force in our x direction is equivalent to our spring constant, the negative of our spring constant times x, the function of x actually, so x of t. The f of d portion right up here is equivalent to negative b times the function of our velocity, and then f of t is equivalent to this term right up here. So we get that f of t plus fd plus f net in the x direction equals mass times acceleration. So once we plug all of those in, we can get everything onto this side, so this term and this term, and then we have this equation up here. So in this, it says that we're assuming a solution of the form x of t equals our amplitude times cosine of our angular frequency times time plus our phase constant. And in this case, our phase constant is 0. So we can plug all of this in right here, where it gives us this. It wants us to write acceleration and velocity, the functions for those, as derivatives of x. So velocity is the first derivative of position, so it's equivalent to our angular frequency times our amplitude times sine of Wt plus our phase constant. And then acceleration is equivalent to the derivative of our velocity function, which is negative w squared times our amplitude times cosine of Wt plus our phase constant. So we also have to explain why W equals Wd in this solution. And the reason for that is that both, you can see over here, both equal the square root of our spring constant divided by our mass, which are both constants, so they never change, so they're always equal to each other. And then we also want to figure out what we know about the sum of the mass times acceleration plus b times the function of our velocity. So down here we can write that. We can multiply mass times our acceleration equation and b times our velocity equation, and we get this, and we see that we have a cosine and sine, and then a bunch of constants right in here. Yeah, not really 100% sure what I am supposed to figure out about that, but that was part of the question. And then we have to explain why this problem is not easy if the driving frequency is given by, is only easy, sorry, if these two are equivalent to each other. And that's because when we're solving this, if this is not equal to this, we can't take the derivative because it's going to be a different number. So that is how you do number 3. It mostly deals with force and a little bit of applying integrals and derivatives to finding velocities and acceleration. So yeah, that is how you do number 3, and thank you for watching.